So we began talking about titrations. Typically titrations are used to figure out the concentration of some unknown acid or base. And we're not doing unknown situations, we're just kind of looking at mathematically the process of going through an entire titration and identifying a few points. We talked about midpoint or halfway point, we talked about equivalence point. We got through some of the titration problem, but essentially in this very first problem that we began doing, what we began doing here is we had a weak acid and we titrated it with a strong base. So basically we added a strong base into that weak acid solution, and we did a few things. Okay? Before we added any of the strong base, we treated it like a what kind of problem? We treated it like a weak acid problem, because all that we had there was a weak acid. Yep. Then after we added some of the strong base, what did we treat it like? A buffer problem, because what happened was we had our acid and it reacted to completion with that strong base. To give us some acid and some of its conjugate base, which was just like what we did when we solved for buffer problems. Correct? We did stoichiometry first. We reacted all of our added base to completion. Then we used the Henderson-Hasselbalch equation. Okay? We did that for a couple situations. Okay? We did it for 2, 3, and 4. One important thing to make note of was 3 was a specific point that we talked about. What was that point? Right, it's the midpoint. And the midpoint isn't necessarily when we have half the volume, it's when we have half the moles. Remember me stating that. If we have half the moles, then half of this will get reacted, leaving you with the other half in the base form, so that the ratio is what? 1 to 1. And when we're at the midpoint, we can assume that the pH equals the pKa. Why did I say it doesn't necessarily mean half the volume? It can mean half the volume. If what? Remember? Yeah, the molarity could be different. If the molarity is the same amount, then if I have half the volume of my base added, I will neutralize half of my acid. But if I have different concentrations, then my mole numbers aren't perfect. And they're not going to work out so that you react half. For example, if this was 0.2 molar, that would be my equivalence point, because 25 times 0.2 is 5. Okay. Put that in your calculator. Yeah, that's 5. You don't have to do that. So we would have had 5 millimoles of this and 5 millimoles of this, and that's actually our equivalence point when we neutralize everything. So if the concentrations aren't equal, then we cannot say the midpoint is half the volume. If the concentrations are equal, we can make that assumption. Okay? So if this is 0.2, what would the volume need to be to reach my midpoint? Or half. Right? 12.5 times 2, 0.2 will give me 2.5. That makes sense, everybody? So Be careful. Don't go so fast that you assume, oh, half volume, so therefore midpoint. Okay? Then we got to step 5 and we stopped. So this was really 2 through 4, was using that equation. The first step was doing just a weak acid problem. And then we got into number 5, which we said was the equivalence point. And what did I say was the definition or meaning of the equivalence point? Yep, when you've neutralized your initial acid or base that you had at the beginning. So in this case, I have acid at the beginning. When I have completely reacted all of that acid, I am said to be at my equivalence point. Okay? Now, for a weak acid or a weak base titration, this is not a pH of 7. And I'll show you why. Okay? Now, number 5, we have 500 milliliters of 0.5, which would give me 5 millimoles of this and 5 millimoles of this. Everyone's seeing it, so I don't have to write it all down. Okay, those are going to do what to each other? Cancel each other out so that I have how much here? 5 millimoles. So essentially then, I have to treat my equivalence point of a weak acid problem like a weak base problem.
Do you always do that at the equivalence point?
Yeah, if you, well, right now we're titrating a weak acid.
Yeah, but you
So if you start with a weak acid, at the equivalence point it's a weak base. If you start with a weak base, at the equivalence point you're doing an acid problem. Does that make sense, everybody? When we get into strong base, strong acid titrations, those are a little bit different, but those are easier. So, I have a weak base. So this is what your equation will look like. There's your weak base. What is the acid that it's going to react with? H2O. I don't have any of this anymore, right? Now I will produce some of it. So does that make sense for an equation for us here? Okay. Now we are going to treat this like a regular weak base problem with one little exception. Okay. I know how many millimoles of this I have, but I do not know what the molarity of this is. And I am going to kind of go back to the ice table here just to kind of show you this. We know I have 5 millimoles, but when we do these equilibrium ice table problems, don't we want molarity? So we're not doing a buffer problem anymore. I cannot just put in millimole numbers. Does that make sense? So how would I find the molarity of this? What? What is molarity? Let's start there. Okay. So if I have millimoles, could I divide it by my milliliters? Now the question is what is the volume that I currently have here? Okay. No. How much should I start with? How much did I add? How much do I got? Everybody understand why it's 100? I started with a weak acid solution that had 50 milliliters. And then I added another 50 milliliters. Okay, so that will give me a concentration of 0.5. Okay, and technically these are 0 and 0. Now I'm not gonna write probably the rest of the stuff out. You probably can figure it out up to this point. However, we do need one more thing before we plug in and solve for what the x is. What other thing can we not forget to do?
Oh, this is K, KB.
Yep. Okay, A needs to be converted to KB. So our KB is KW divided by KA. KB is and now what would we do to get our x then? Just like we've been doing for a while. Concentration, right? Right, out of the way now. Could maybe put it in there, but I realize I probably didn't give you a whole lot of space. I tried to give you at least a half a page. The Gripper brothers might be not enough, but. Now, let's be careful here. My x when I solve for it is,
Why does it
oh, I wrote that wrong. 5 divided by 100 is 0.05. So I wrote this one wrong. Sorry guys, you guys might want to make that change. Okay. X then. Now what is your x? OH in this context. So, we had a little bit of stuff we had to do when we're at the equivalence point. We now are a weak base, we had to change Ka to Kb, and at the end we get an x that tells us OH, which we need to convert to H plus to take the negative log of that. And again, there's a couple ways you could do it. You could take this and convert to H plus, then negative log, or you could go negative log to find POH. And then your pH is 14 minus that, which I don't know off the top of my head what POH is. And maybe you guys prefer doing it the other way. pH of 8.73 approximately. Now, here's what I want to note about the equivalence point when you start with a weak acid. Wouldn't hurt you to move this maybe right there.
It's too late now.
Well, it's never too late. that in your notes or not, but that's kind of important to make to remember or recognize that when we are doing a titration of a weak acid, our equivalence point will always be greater than 7, because yes, we no longer have any of our weak acid, but what we did was convert a weak or a strong base into a weak base. So there's a lot of weak base remaining at the equivalence point. That's why our solution is going to be basic at the equivalence point. Does that make sense? So what do you think will happen then at the equivalence point when we are doing a titration of a weak base? It will be less than 7. And when you do a neutralization or a titration of a strong acid with a strong base, the equivalence point will actually be 7, which we'll find that out tomorrow. Okay? Questions on the equivalence point here? Any? All right. Then we've got above the equivalent. Number 6. Okay? So let's imagine then 60 milliliters. Okay? I will have my OH that is given off by my weak base, and I'll also have some OH from my strong base that doesn't get neutralized or switched because I don't have any more acid to react with it, correct? So I technically have 2 places that give OH. I have this reaction that gives OH, and then I just have the sheer dissociation of this giving OH. Okay, now here's something that you might want to write down. It's very important. We have our 2 bases. What do you think we're going to do based on that? Any ideas? This is the amount of OH minus that was given off due to that base. Right? That's the concentration of it. Okay? If I add 10 more milliliters, okay, first off, how many millimoles of NaOH will I have if I have 0.1? 6, right? So I'll have 6 millimoles of OH minus. Okay, but we said we neutralized how much of it? These all tough questions. What? And how much is all of it? asking tough questions? Confusing questions? I have 6 millimoles. What did we just get done talking about that happened to that OH? What? Okay, that's true. But didn't it react at the beginning? And eventually, at the equivalence point, it all reacted. So I didn't have any more weak acid left over. So how much weak acid reacted with it? How much did we say? Well, how much is all of it? 5. Right? I don't have any more weak acid. All I have is 5 millimoles of weak acid that I can react with it. So I should have how much millimoles of OH minus that doesn't get reacted? 1. Okay? 1 millimole of OH minus that doesn't get reacted because the acid's completely gone. Well, in order to find the pH, I need to know the concentration. So just like earlier, divide by 110. Why 110? You guys added an additional 10 more to what we just did. That'll give you 9.1 times 10 to the negative third as my molarity of my OH minus. Now, let's compare that number to the amount given off by my weak base. Do you see it? If I add this to that number, is that going to change that number really at all? So, what I'm trying to show you here is, once you get beyond the equivalence point, all you're worried about looking at is the strong base that you've been given at the beginning. Because the strong base is going to give off way more OH minus than a whole bunch of weak base will. So, once you get above the equivalence point, all you need to do is figure out your concentration of remaining strong base. Negative log of that gives you POH. And then your pH is 14 minus that. So, negative log. Therefore, your pH is that. Oops. I feel like we don't have quite as good a grasp on this as I had hoped. Let's walk through it slower from the beginning.
Why don't you have to do like the whole, like for 6 you just did, you found the molarity of OH.
Why did I do that for 5? Well, all of my OH minus got reacted in 5.
So you have to find the X.
So, yeah, let's go back to 5. Okay? I had 50 milliliters, so I ended up having 5 millimoles of my strong base. That 5 millimoles got completely reacted with the 5 millimoles of my weak acid. Does that make sense? So I didn't have any OH minus due to the strong base. Does that make sense? It all got completely reacted. Well, it all got reacted to produce a what? A weak base, correct? We know a weak base is going to give off some OH minus, right? So we had to then set up a weak base problem because I had a bunch of this, which it will react a little bit with water. We know it won't react a lot because weak bases don't what? No, they don't completely dissociate, they only slightly dissociate. So it's only going to give off a small amount of this. Okay, so yes, we completely got rid of all the OH minus from our strong base, but as a result, we had a weak base which can still give off a little bit of it, and that's why we're always going to see a pH greater than 7 when you're doing a titration of a weak acid. Does that make sense, Graham? Over here, because we added more than the amount that we can neutralize, it only was able to neutralize 5 of the 6, leaving us with a whole millimole left over, which is still a lot more than can even be given off by my weak base. Does that answer your question well enough?
You do the same thing for 7?
Yep.
So the 2.5.
Yep, so this would be 7.5, minus 5 would be 2.5, and then you'd add the different volume though, right? 125, so it'd be 2.5 divided by 125, it would give you a concentration of OH minus, negative log, you get POH, or you could do the H plus route as well. And yes, why don't you guys do that real quickly? So if you can break these problems down into the chunks before anything's added, when stuff is added before the equivalence point, at the equivalence point, and beyond the equivalence point. There are really 4 sections.
Is there an
Equation.
or like, a reaction?
Well, technically, we still have this, but it doesn't give off enough OH to be meaningful comparative to the amount of additional OH from the strong base that we have. Does that make sense? So technically, if you want to say what is our equation, well, it's just the breakdown of my NaOH into that. Does that make sense? Because it's a strong base, and so therefore it's going to completely dissociate. Did you get a pH for the last one? I don't even have an answer for it. So. Did you guys get the same? What'd you get? 12.3? 12.3? Really? Only 12.3?
So can you pretty much like follow this pattern for all?
Yes.
I mean, obviously the numbers might not be the same.
Yeah, the numbers are going to be different. You might not have identical concentrations. So yes, the same pattern, absolutely. And even when we start doing a weak base, it's a similar pattern, just flipped. Like if I start with a weak base, my first step before anything is added is a weak base problem. After I've added some strong acid, it's a buffer problem up to the point where we get to the equivalence point, right? Once you get to the equivalence point, that's where you flip from a weak base to a strong acid. And then beyond that, you would treat as just a strong acid. That makes sense? So there are really 4 points. Before you add anything, you just treat it like the problem it is. After you've added, but before the equivalence point, it's a buffer problem. At the equivalence point is where you flip from what you started with to what you're ending with. You do have to take into consideration this. You've got to get the correct molarity with the total volume. You've got to remember that you've got to flip the Ka to Kb or Kb to Ka. Does that make sense? And then once you get beyond the equivalence point, that's your 4th kind of step, where you're only focusing on what your strong thing is. Now, it could be strong acid or strong base, depending on the problem. And then we said that because the strong is going to give off way more than the weak will, we can ignore the weak and just focus on the strong stuff. That make sense? So, the next problem just has a couple points along the way. So before I even get into doing a problem, let's just see if we can identify some things. Okay. We are still doing a weak acid titration. This is what our conditions are. And we are still adding a strong base. So same process as the previous one, different Ka value, different weak acid. Thankfully they gave us the same concentration. Let's first identify what type of problem this is.
Oh. Usually at HCN.
Yes. This is after something's been added, right?
Oh.
So it's a what type of problem? It's a buffer problem. You see what I'm saying? If it was before anything was added, then your first step, yes, would be a weak acid problem. Okay? This says we're at the halfway point, so we didn't have to even identify what the halfway point was. Guys, number 2 should be really easy. If they tell you what is the pH at the halfway point, what should you immediately do? Right? If that's all they want, they don't give you numbers where you actually have to figure out what the halfway point is. If they just say, hey, what's the pH at the halfway point? Easy. pH equals pKa, because at the halfway point, what's the ratio? 1. And so log of 1 is 0, so pH equals pKa. Then you would just say your pH then ultimately is negative log of your Ka. pH at number 2 is wow. Okay. That's a really weak acid. It said it is a very weak acid. It wasn't lying. Very weak acid. Okay? So weak that at my midpoint I have the basic.
So at the midpoint, pH equals pKa?
Because remember, the midpoint is when I have, so I could show this all up here, right? I've got my weak acid. It's going to react with my strong base to produce this. Sense? Okay? Now they didn't give us what the volume was, but if it's a 0.1 and a 0.1, we know that the volume had to be 25. Which would have given me 2.5 millimoles of this. Nope, sorry. I started with 5 millimoles. And then 2.5 millimoles of this. So when we do our stoichiometry, what we're left with is 2.5 of this. And 2.5 of this, so when we plug it into our Henderson-Hausbach equation, we get a ratio of 1. Does that make sense? When you have a ratio of 1, your log of 1 is 0, and so your pH equals your pKa. So, we got 5 minutes. You want me to kind of run through these guys really quickly here? Okay? I should have left that up there, that equation at least. Alright, so we had HCN. Does everybody understand the reaction here? Because sometimes that's half the battle, identifying what's reacting. Got my weak acid, and I'm introducing a strong base, so that's why this is the reaction. Okay, we said that this first step is a buffer problem, and in all buffer problems, what do we have to do before we use the Henderson-Hausbach equation? Stoichiometry. Okay. 50 times 0.1 is 5 millimoles. So can somebody, well, I'll just look it up. 8 times 0.1. 8 milliliters times 0.1 is, wow, why am I even 0.3? right? Do what? Subtract. So after I should have 4.2. And over here, 0.8. After done with stoichiometry, I take those numbers and plug them into what? Pk is 9.21 plus log of base over acids, 0.8 over 4.2. When you solve that, you should get 8.49. Now, this is a unique problem in that we did a very weak acid, so it didn't take long for the base to get it over a pH 7. Okay? Because remember, if this is a weak acid, its conjugate base is actually kind of strong, right? Not like strong, but a strong version of a weak base. Okay, so that's the answer to A. Now B, remember there are those 4 stages. We got to identify what stage we're at. We're at the equivalence point, so how are we going to treat this problem? Okay, so what do we start as? So this is going to be a weak base. Okay. What is my base in this situation? No, I'm talking about conjugate of my weak acid. CN. Right, because we got rid of, at the equivalence point, we've neutralized all of my strong base, correct? What will the CN react with?
H2O.
Okay. And we are going to get some OH left over, and that's where our pH is going to come from. So I got to first take my Ka and turn it into Kb. Your Kb is 1.6 times 10 to the negative fifth. Now, gotta be careful. This is the same starting amount we had in the previous problem, so I have 5 millimoles of weak acid, right? That gets completely neutralized to produce 5 millimoles of my weak base, right? But I need to divide that by what? Looks like, yeah, it's going to take 15 milliliters of the other guy. So yes, 100. Don't always think it's 100 though, right? So there's my concentration. I could set up an ice table, but once I know my concentration, we can use the shortcut, which says that my X is going to be my Kb times my initial concentration. And what's your X telling you? OH. So then you got a little bit of work to do to get to your pH. But to save time, I'll just give you the pH. You guys know what you have to do to get to your pH, right? You have to convert OH minus to H plus and take negative log of it, or do negative log of your OH to your POH, and 14 minus that to get your desired pH. So, this little handout that I gave you on Friday kind of gives you the stages Now, will every problem in your homework have all 4 stages? Maybe not. I mean, this one only had 2. Right? Because even this guy is still a buffer problem. But it's our simplified buffer problem because it's at the halfway point or the midpoint. So we never did one at the very beginning before any was added. We never did a problem after the equivalence point. Okay, so break it down into these 4 problems if you can. Honestly, the hardest is at the equivalence point and beyond because that's where you have to do a little bit of thinking. You have to figure out the total concentration and you gotta flip some stuff. Right? If you have questions, come see me after school. At any time you can come in and check the workbook. I don't care.
Too many. I've literally had 3 like my entire life.
Yeah, well, I have like 3.5 years, so I just have that many identities.
Who are you really? Which of your emails are you